And so now let's begin. If you guys have any specific you want us to cover before we start with module 7, please let me know. So, and again, remember your exam covers module 7 through 9. So your gas laws, your thermodynamics, so your work, heat equations, and enthalpy. So I want to start off on page 191 of your workbook, where it's the unit review. And I want to start off at the very top with number 23. So also, if you guys need any help, feel free to use your mic, or if you're a bit too shy about that, you can ask your question in the chat. Andre here is another peer leader that can help you out if you have any questions, and more peer leaders will come in soon. So if you have any questions, feel free to ask them. But for now, let's start off here on page 191 of your unit, I believe it's unit 3 review for number 23, which is involves your gas law. So saying that we have a sample of 2.5 times 10. So we have a sample of 2.5 times 10 to the power of 3 grams of carbon monoxide gas. And it's held near room temperature, which is 20 degrees Celsius. And in a hyperbolic chamber where the pressure, just telling you where it is, where it tells us a pressure of 191.5 kilopascals in a closed system. So in a closed system, and it's saying what volume does the gas occupy in the system. So we're looking for a volume. So out of all the things that this problem gives us, we see that we're given a mass, we're given temperature. Let me fix that. And we are given a pressure. So we're looking for a volume specifically. So who remembers, who can tell me what equation can we use with the information we currently have in order to find volume?
We use the STP equation.
Sorry, can you repeat that?
STP?
Not STP. Remember, STP is standardized temperature and pressure, meaning you're going to have a constant temperature and a constant pressure unless stated otherwise. So that's more of just a condition, not an equation. Let's see. So like Miguel said in the chat, PV equals nRT. So here we have a pressure times volume is equal to moles, your gas constant times temperature. Now, remember, really quick, since we're working with this equation, what does the gas constant equal to?
0.821.
Perfect. 0.0821. And what are the units involved with the gas constant?
Joules, Kelvin, moles, and ATM?
No, in this case, we're not dealing with joules here. So remember, if you guys are going to look up the gas constant, be careful by looking very specifically, because this gas constant, the specific one we're looking at, is liter atmospheres. So liter times atmospheres over or divided by mole Kelvin, or moles times Kelvin. Since our gas constant has liters, atmospheres, moles, and Kelvin, then the rest of our values must have those units. So are my values that I have currently in these units? Yes, I see you shaking your head. Right, it's not. So let's see here. So what can I do? What can I do to start converting what I have into these values? Let's start off with what we have here, which is grams of carbon monoxide, CO. What can I convert this into to a unit that we need that's in the gas constant?
Moles.
Perfect, moles. So let's just make our N moles. So it says we can convert grams to moles. How can I convert my grams to moles of carbon monoxide?
With Avogadro's number?
Not quite. Remember, Avogadro's number is converting from moles to the number of molecules, atoms, or formula units. So there's a step before that.
Divide the 2.5 times 10 to the third by the total mass of CO.
Not the total mass, but the molar mass. So you are right. It's just called the molar mass. Perfect. So 2.5 times 10 to the power 3 grams of CO. So we need the molar mass. And remember, molar mass is, the amount of grams per every 1 mole of that substance. So like Savannah said, if it's the total mass of the molecule, what will be my molar mass of carbon monoxide?
28.011.
28.011. Everyone agree? Anyone disagree? Let's see. So it's 28.011, or you can put it as 28.01, or just 28, since it rounds it up pretty well. So this is grams per mole. So what do I need to do in order to cancel out these grams of carbon monoxide to be left with moles? Does my 28.011 go at the top or the bottom?
It goes in the bottom.
Perfect. So we have 28.011 grams. Since the ratio, since we have grams at the bottom, and this is per every 1 mole of the substance, we have 1 mole of CO, carbon monoxide, on top. So our grams of carbon monoxide cancel out, and now we're left with a unit of moles of carbon monoxide. So now that I have the unit that I want, all I have to do is to multiply across and divide by the bottom. And what is now my new unit, or I guess my new number for my moles?
89.25.
89.25, and that would be moles of carbon monoxide. Perfect. And let me check real quick. Perfect. So now we have moles, so we can move on to the rest of what we have. So I have temperature that's in Celsius, but I'm working with Kelvin. So because of my gas law here, or my gas unit. So how can I convert my Celsius into Kelvin?
At 273.5.15, I mean.
Perfect. You could do that, or just 273. Either one works. If you want to be very specific, you can go with the 0.15. So we add 273 to our Celsius, and that will give us 293 or 293.15. I like to round things up a little bit sometimes. Kelvin. So now we have Kelvin. Let's move on to the rest. Here we have our pressure that's in kilopascals, but I need this to be in atmospheres. So how can I convert from kilopascals into atmospheres? What's like my ratio between those two?
1 ATM equals 101.325 kPa.
0.325 kPa. Perfect. So this equal sign is your ratio. So your top equals the bottom. So perfect. And you can swap them out vice versa. So with that, I have my 191.5 kPa. And which of these values goes on the top and on the bottom in order to cancel out kPa?
Kilopascals goes on the bottom.
Perfect. So 101.325 kilopascals, kPa, over 1 atmosphere. So our kilopascals, they cancel out, and we're left with atmosphere. So what is now my new pressure in atmospheres?
1.89.
Can you repeat that again, sorry?
1.89.
Perfect, 1.89 atmospheres. So let me quickly clear this up. So now that we have all our values that we need, let's first isolate the variable that we're looking for, which is volume here. So if we have our PV equals nRT, and we're looking for volume, how can I isolate volume before I start plugging in anything in?
Divide by P.
Perfect, we divide by P. So if we divide by P, our pressure, by moving it to the other side, we're left with volume is equal to nRT over P. So now that we've isolated the unit that we're looking for, so everything that we have, we can just add it onto the equation. We can now do that. So we now have V is equal to our moles. So 89.25 moles. Let me just move this to the side so I have room. So moles times our gas constant, which is 0.0821 liter atmospheres over mole Kelvin, times our temperature in Kelvin, which is 293 Kelvin, all divided by our pressure as shown here, which is 1.89 atmospheres. So before we start, multiplying and dividing the numbers, we need to make sure we're left with the unit that we're looking for, which is liters, because here we're trying to get volume. So what units can I cancel out right away, or that you can see that I can cancel out?
Moles and Kelvin.
Perfect, moles and Kelvin. And can you do you know why we cancel out these units like this?
Because with the 0.0821, moles and Kelvin are the dividend, or yeah. So you're multiplying with mole and Kelvin, well, 0.0821, you're dividing by mole and Kelvin.
Perfect, exactly, because technically these are in the denominator position, whereas these moles and Kelvin here are whole numbers. So it's basically you're dividing technically by the same number or the same unit, so they'll be canceled out. Perfect. So following that logic, what other unit can I cancel out?
ATM.
Perfect, because here this ATM is in a numerator position, whereas this one down here is a denominator position, so they'll be divided and they'll be canceled out. So we're left with liters, which is perfect because we're looking for a volume. So now that I've canceled out my units and I'm left with the unit that I need, what will be my final answer for my volume?
I got 1136.53.
1136.53. Let me erase that point. 0.53. Did anyone get something similar, or did anyone get a different answer? 1136.53. This is liters, not a 2. So if no one disagrees, if we were to look on our workbook on page 191 to see one of the options, we're given 3 options where it's 3341.9, 11.21, 12, 13.63, and lastly 1136.02. So the answer for the number 23 here would be D, which would, even though it's not the 0.53 at the end, it's still very close. So you can count that correct as well. So your final answer would be D, or roughly in the range of 1136.53, or in your workbook, which is 0.02. So perfect. Does anyone have any questions or any concerns regarding any of this? No? Perfect. So let me clear this up. Sorry, it's very hard. I don't know why Microsoft is giving me issues. Perfect. So let's move on to the next question here. So let's move on to number 24, where, let's see here, I can fix this. 24, where it's telling us that air is normally is found to be 78% nitrogen. So we have the composition of air, which it tells us is 78% nitrogen, 21% oxygen, and 0.9 or 0.9% argon, and has a negligible 0.1% of trace gases, so 0.1 of negligible air. So I'm just going to put NEG for short. And then saying that a certain sample of gas is found to consist of, I'll run right up here, of 156 grams of nitrogen gas, so N2. And then 42, let's see someone in the chat. Okay, so we're on page 191 of your workbook, so we're using the unit review questions for this review. So on page 191, number 24, if you want to follow along, they'll be there. And for when we cover the thermodynamic question, that's going to be the next unit over, so unit 4. So it was right after module 9. So we see here that this is going to be our sample here of air that we got. That happens to be, let me fix this 5. Again, it's 156 grams of nitrogen. Where was I? 42 grams of oxygen gas and 11 grams of argon. And it's asking us for what is the mole fraction of argon gas in this sample. So we're looking for the mole fraction of argon. So really quick, who remembers what a mole fraction is in terms of the gas loss?
Is it when you put all the moles together and then you put it over the, okay, so let me get this start over again, right? So you have the moles together, then you get a mole and you divide it by however many moles there are, and that's the percent, or no?
No, you're on the right track. Yes. So remember, so the mole fraction is the amount of moles within the substance. So remember, our sample has a total mass, right? So it has all these masses of, we have nitrogen gas, we have oxygen gas, and we have argon gas. So when we're trying to find the mole fraction, we're almost trying to find the percentage of it. So we're trying to find like a division between like the moles of our gas over the total number of moles of our sample. So what we can do here is, so if remember, we're given this context for a reason. So, the air is always going to be like 78% nitrogen, 21% oxygen, 0.9 argon, and 0.1 negligible gas. So what's the first thing we can do here that you guys have an idea of finding a fraction of this argon gas?
Putting 0.9 over 100%?
So let me do that. Well, technically this is a percentage already, because, oh, you mean divided by 0.9, right?
0.9 divided by 100, or?
So 0.9 divided by, okay, here, let me quickly do this. So you're saying we do 0.9% divided by 100, and that'll give us, the number we would multiply in order to get that 0.9%, which is 0.009. So what would you do now with this number?
Multiply that by the grams?
The grams of argon?
Of argon, yes.
So I'll show you where I like how you're kind of on the right track, but not quite. So remember, this number, the way we get these percentages is by multiplying, say, so this 0.9 being 0.009 to make it a percentage, is we get it from multiplying it into our total sample. So our total mass of the sample of what that certain percentage is out of. So let's take a different path, because you were kind of on the right track. So remember, we're trying to find how much moles of argon are within the whole sample. So let's see in the chat. Exactly, we would need to convert to moles. Exactly. So if it's a mole fraction, we need to find the total number of moles first. So so like saying convert to moles, let's convert all our moles of our substances within the sample from grams into moles. So will be my 156 grams of nitrogen gas, then our 42 grams of oxygen gas, and 11 grams of argon. So what would that be in moles? Who can tell me how I can do that? Let's see here. Perfect. You divide by the molar mass. So remember, we're working with molecules here. They're diatomic, well, except for argon here, it's an atom. But for nitrogen and oxygen, remember, it's going to be double the molar mass you see on the periodic table, because there's two of them. So do remember that. So if we divide by the molecule's molar mass, remember, argon is just one atom. How many moles of nitrogen do I get?
5.57.
Can you repeat that again?
Yes, 5.57.
5.57. Let's see. So did you divide by the molar mass of nitrogen gas, right?
Yes.
So remember, it's going to be this 156 grams. So let me 156, because I got a different number. I'm trying to see.
I did use 14.007. I don't know.
Let me see, because either way it shouldn't be that. Oh, I see. Okay, I did something wrong there. Okay, I forgot to include some parentheses. So you are correct. So remember, when you're calculating this, remember where you're putting your parentheses. That way it counts the whole thing, not just one number and then multiplies it by another. So yeah, 5.57 moles of nitrogen gas. So now what about oxygen? Who can tell me the number of moles of oxygen from this sample?
1.31.
1.31, perfect, moles of oxygen gas. And who can tell me how many moles of argon gas do we have now?
0.275.
Perfect. So 0.275 moles of argon. So now that we have all our moles of each element, or I guess each compound within our substance, what's the next thing I would need to do? Who has an idea?
Add them.
Perfect. Since we're trying to find a fraction, so so perfect. Yeah. So we would add them all together because we need a total in order to divide by the amount of argon we have, because we're looking for a fraction, the mole fraction of argon. So if we were to add all this together, what would that give me?
7.155.
7.155. Perfect. And this is our total moles. So total mole. Total moles. So now that I have my total, what can I do now with my total?
Divide 11 grams by the total.
So we're
Or
dividing.
your mole.
Exactly. We divide by moles. Remember, if we're looking for mole fractions, we need to work with moles, because if we were dividing grams by moles, we end up with a weird molar mass. That doesn't make sense. We have a whole sample being divided by our 11 grams. So let me come down here and erase this real quick. So we take our moles of argon, which is 0.275 moles, divided by our total moles. So we have 7.155 moles. And what would that give me?
3.84 times 10 to the negative 2.
Times 10 to the negative 2. Perfect. And really, this doesn't have any units because our moles cancel out. It doesn't really matter. But this here, this would be our mole fraction for argon. And if we check the choices here for number 24, we see that for A, it is 3.8 times 10 to the power of negative 2. So our final answer, not B, it'd be A. I don't know why I wrote B. So yeah, perfect. So this here would be your mole fraction of argon. Perfect. So does anyone have any questions, any concerns regarding mole fractions or what we just did with PV equals nRT?
So it's not exactly like that, right? But it was like one of the questions on the homework kind of got me confused. It was 50 milliliters of nitrogen at 25 degrees Celsius and a pressure of 736 millimeters per mercury. What is the volume of the temperature if the temperature increases by 35 degrees C? I don't know if you need me to repeat that or.
Yeah, so here, let me clear this up. Oh. Yeah, so let me clear this up. So can you repeat that again?
Yes. So the problem says a container holds 50 milliliters of nitrogen at 25 degrees C and a pressure of 736 millimeters mercury. What will be its volume if the temperature increases by 35 degrees C?
So its volume if temperature increases by 35 what again, sorry?
Degrees C.
Degrees C, okay. So, oh, my bad.
And it's also, the initial temperature is 25 degrees C.
Okay, so we have an initial temperature. So Ti is equal to, can you repeat that again, sorry?
25 degrees C.
25 degrees C. Okay, so this involves another equation. So let me see, something in the chat. So perfect. So, okay, so remember, like your PV equals nRT isn't your only equation, right? Remember your gas laws, right? Because you have your Charles law, your Boyle's law, your Gay-Lussac's law, but you also have a combination of these laws, which is known as the combined gas law. So, because here we're given, because here we're looking for a final volume, right? If that's our V2, right?
Yes.
So here we're given an initial volume. So our V1, we have an initial pressure, initial temperature. So remember the combined gas law. So where it's going to be your PV, so P1 V1 over T1 is equal to P2 V2 over T2. So let me write this so it's a bit neater.
Also, it's a 736 millimeters mercury.
Oh, 736. Okay.
I guess I cut out sometimes.
It's okay, don't worry. So 736 millimeters of mercury. So here, if we're working with this P1V1 over T1 equals P2 V2 over T2, we notice that we're missing a P2 here. So what can I do in order to solve for this P2 using your other gas laws? Let's see here.
We could use P1 over T1 and P2 over T2.
Mm-hmm. So to answer your question real quick, Luisa, it won't be on Blackboard, but it will be in the Peer Leader, like this review session will be in the Peer Leader YouTube channel. So I don't know if one of the peer leaders can link that in the chat, please. So this will be uploaded later tonight because granted, it does take time for the video to render afterwards and then to upload the rendered. Mm-hmm. So it will be there for anyone that wants to visit it. Mm-hmm. Perfect. So going to what you said, Sebastian, it's going to be your P1 over T1 is equal to P2 over T2. Since we were looking for P2, we need to use an equation that involves P2, right? And using this gas law, let's plug in what we know and what we already have here. So let me just quickly double check some stuff. Perfect. All right. So let's plug in the values that we know so far in order to find for P2. Well, actually, before we do that, let's isolate P2. That way we're not confused on any part. So how can I isolate my P2 here?
You can multiply that by T2.
Perfect. So we multiplied it by T2. Onto the other side, we're now left with P2 is equal to T2 times P1 over T1. Perfect. So now that we have that, we can now go and plug in our values that we have so far from this problem. So we have our P2 is equal to, we have 736 millimeters of mercury over, well, it doesn't matter where you place them, you're going to be multiplying it anyways, over, which is our T1. So we have our 25 degrees Celsius times our T2, so 35 degrees Celsius. So really quick, notice how I didn't convert anything into Kelvin or atmospheres, right? So when it comes to something like this, whenever your problem is not specifically asking for those units to be converted, it's okay to work with the units you have as long as you're canceling out the correct unit. It's only when you're working with PV equals nRT when you have to convert to Kelvin and atmospheres because your gas laws, your gas constant has liters, atmospheres, moles, and Kelvin. In this case, we just need to have everything be the same unit to work. So when we plug in our values, we have this. So what unit can I cancel out from this operation?
Celsius.
Perfect. I can perfectly cancel out Celsius. And I'm left with millimeters of mercury. So what is now my new P2 by solving this operation?
(1030.4).
Perfect. 1030.4 millimeters of mercury. So now that I know what my second pressure is, or my final pressure, my P2, let me just zoom out a little bit to show. Now I can now plug this into my combined gas law, which is my P1 V times V1 over T1 equals to P2 V2 over T2. So if I'm going to be working with this, my P1 V1 over T1 equals P2 V2 over T2. Let's isolate my V2 since that's what we're looking for, our final volume. So how can I isolate my V2?
Multiply both sides by T2 and divide by P2.
Perfect. So let me just write this in here to know that we have it. So like you said, we multiply by T2. And then we end up with T2 times P1 V1 over T1 equals to P2 times V2. And like you said, divide by P2, so our final pressure. And let me quickly add a new page here. Perfect. So then let me write it up here. So we have our new equation where we isolate V2, where V2 is now equal to, so we have T2 times P1 times V1 over T1, all being divided by our P2. So now that we have everything where we want it to be, where we successfully isolate V2, we can now plug in the values that we know and have. So we have V2 is equal to, so we have our final temperature, which is 35 degrees Celsius. Let me fix that so it's not as ugly. So 35 degrees Celsius times, so we have P1, which was 736 millimeters of mercury, times our initial volume, which was 15 milliliters. This operation being divided by our initial temperature, being 25 degrees Celsius, which again, all of this will be divided by our final pressure, which is P2 of 1030.4 millimeters of mercury. So now that I have everything plugged in, let's solve this a bit step by step real quick. So what units could I cancel out right on the top?
You can cancel out Celsius.
Mm-hmm.
And then you can also.
Oh, go ahead.
All right, and then you can also cancel out millimeters mercury.
Perfect. Since in the end this will become a numerator position up here, it'll cancel out with this denominator millimeters of mercury. So since I'm left with a volume of milliliters, that's perfect. So by solving this operation, who can tell me what answer do we get from here?
15.
So did you see 15? Did you say 15?
Yes.
15. So let's double check that. So anyone disagree? Anyone agree with that answer? 15 milliliters?
The same thing.
Same thing? Perfect. Okay, for perfect. Let me check. Just I need to double check myself. Let's see, 736. Oh, my bad. Sorry, it's just my calculator is being weird because I keep getting different numbers. Let's see here. Anyone else got the same answer or something different? Let's see here. Yeah, same answer, same answer. Perfect. Let's see. It's weird. I keep getting 25 on mine for some reason. Let's see. What am I dividing by wrong? Oh, I see. I divided this by 15, not 25. Okay. So yeah. So here we have our 15 milliliters, but on the book, seeing as it's number oh wait, no, not the book. That's right. It's the for the homework. That's right. My bad.
Mm-hmm.
So in the end, depending if it asks, does it ask you for your answer in liters or does it just tell you for a volume?
It doesn't have any
Specifications?
I forget what to call. There you go. Yeah, it doesn't have any specifications.
Okay, perfect. Yeah, so it's not specifying a specific unit of volume. Then this here would be your final answer. All right.
Cool. Thank you.
Perfect. All right. So, okay. So that's. Oh, go ahead.
I was wondering if I get volume 2 first, then like before pressure 2, should I get the same answer for both, or there's a specific order that I have to get that?
Not necessarily. This is one of the ways because if we look back at other gas laws, remember we used Gay-Lussac's first in order to find our P2 and then use the combined gas law. Because your other gas laws where you have Boyle's, which I believe is your P1 times V1 is equal to P2 V2. But then you also have your, I believe was the other law, I keep forgetting the name, where you have V1 over T1 equals to V2 over T2.
So if I use the last one that you wrote, the Charles law first to get volume 2 and then substitute it in the one that you have on top, would I get the same answer for both values?
You should be able to, yes, because in the end, all these laws like play into each other. Because notice how our combined gas law is a combination of all our laws, right? We have our P1 times V1 right here over our T1, since we have, see, this is P1 over T1 equals to P2 over V2, I mean T2. So we see that
Yes.
again. So we see them all combined. So in the end, no matter what path you take, you should get the same value here of our 15 milliliters.
Okay, thank you.
Perfect. Is this what you got? Did you get 15 milliliters for V2?
Yeah.
Yep, perfect. All right. So that way would have been a shorter way, but I want to show you guys this long way just in case you come up across something like this where you need to like mix around some equations a bit. So that's enough out of me for now. So I'll carry it off to Renee. So you can take over me. Thank you.
All right, for sure. So I'll be going a little bit of Alon, you already covered gas laws and all that, right? All right, do you
Yeah.
think we can go straight to thermodynamics
Yeah, I was
or
gonna say if you can go to thermodynamics. We basically just covered everything about gas laws, which is your combined gas law, PV equals nRT plus your mole fraction, which is typically everything you need to know about gas laws.
okay, well actually then I'll go to work, yeah. So this is going to be tipping
Before we switch, just to be sure, does nobody has any questions on any module 7 stuff? Just so we can make the transition without. Like I said, it's 3 modules, so even if we do go over 8 and 9, we'll probably hopefully have time to go over 7 again anyways, but just to be sure. Nobody? All right, go for it, yeah.
All right, awesome. I can't share my screen for some reason.
Oh yeah, let me make you co-host. Sorry, let me make everybody co-host or the peer leader.
Coolio.
Okay, yeah, you should have.
All right, awesome. All right, so I'll be going over module 8. So module 8 just consists essentially of 3 main equations, all right? So we're going to be dealing where we see this again, negative pressure times a change in volume. We're going to be dealing with Q is equal to ms delta T, change in temperature. And then at the very end of this, which basically these are the same equations, just looking different, we have heat transfer. So that would be one side negative ms delta T is equal to ms delta T. All right, so for most of these problems, or actually all of the problems, we'll be using the review questions. All right.
It should be unit, if you're looking for it, guys, it should be unit 4 right after module 9.
Yes. Okay. So one thing to list in this module is the units have to be correct every single time, or else these equations do not work. So every single time that you put anything into a work equation, so W is equal to negative P delta V, we're going to be dealing with liter atmospheres, and that's the number that you get at the very end of that. Now, obviously, to get there, we need atmosphere and pressure, or pressure and atmospheres. And, of course, we need liters. They cannot be in milliliters, all right? Because if you do that, it's going to be a wrong unit, and your answer will be wrong at the end. The heat equation, so basically the second one refers to how much heat is a substance undergoing, or how much heat is entering or leaving that substance. You're going to get a number in joules, all right? Just a base number in joules. Like, let's say if you ended up with 56 point something something, that 56 is in joules. It's not going to be in kilojoules, it's not going to be in millijoules, all right? To get there, however, we're going to need grams. Not usually used to working with grams, but for this equation, you will need that. S is specific heat, all right? Now, this number will be unique to every single combination of mixture solutions. Basically, if you can think of a different substance, it will have a unique specific heat, and we'll solve a problem trying to dictate which substance something is. And then here, if I do recall correctly, these will be in temperature changes of degrees Celsius, right? Usually we use Kelvin, but the difference between Kelvin and Celsius is the exact same number. So here you're able to use Celsius, all right? And the exact same thing follows for these equations over here. Sometimes they're in megajoules, but you just have to account for that. We're going to do some examples that refer to how exactly you do that. All right, so I hope we're good right now. Let's solve a work problem. So I'm gonna erase my screen. Actually, I'll just do it right underneath. All right. I'm gonna say this isn't in the workbook itself, but I'm just gonna make a problem off the top of my head to show you how exactly I would solve a work problem, not in liter atmospheres, but to joules. So we're gonna have to do that right now. Let's say how much joules of work are required to, let's say, compress a gas from, let's say, 7 liters to 1.2 liters at a pressure of, let's just say, like 3.5 atmospheres. Let's just say that's a pressure of 3.5 atmospheres. All right. Now, if we're trying to find liter atmospheres, we'd only have to do 2 calculations and then we'd be done. However, this equation is not set up for joules. It's set up for that. So we use a conversion factor at the very beginning of this. 1 liter atmosphere is equal to a very familiar number, 101.325. I believe it's 325. Yep, 325 joules. All right, so we're going to use this at the very end. But essentially, we're just going to put all our variables into our equation right here. Now, the very important thing about this one, when you're doing work equations, you cannot forget this negative. That serves a very important purpose. All right, when anything is negative, remember that it's not a negative amount of energy, it's simply the direction of energy. All right, we'll explain that more when we get into enthalpy, but these serve as the beginning introductions for those. So my pressure, simply we're just going to put things into our variables. So I'm already going to have 3.5 atmospheres. All right. And then, of course, we must remember delta V is equal to V final minus V initial. All right. So I'm going to multiply that times, actually, negative 3.15. Cannot forget that before I do that. My final was 1.2 minus my initial, which was 7. All right. And at the very end of this, you're going to get a positive number because remember, pressure must be negative. So 2 negatives combined will give you a positive. All right. We have 20.3 atmosphere liters or liter atmospheres. Doesn't really matter, but just as long as those units are the same. So then, just a bit of dimensional analysis. I usually like using dimensional analysis because it ensures to me that my units cancel out every single time without it doing it in my mind. And I've just found that that's easier for me. So dimensional analysis, your given always goes top left. All right, so liter atmospheres, I'm going to say that 1 liter atmosphere is equal to 101.325 joules. All right, and once you just do that, I mean, basically you're dividing by nothing and just multiplying. So just multiply your answer by 101.325. The final answer for this problem would be 2056 point, I'll round, 0.9 joules of energy. All right. Now this number is positive, and that serves a very, very important purpose. Can anybody tell me what that purpose is? If you have an amount of energy that's positive, what does that tell you about it?
It tells you that heat was gained?
Yes, heat was absorbed by the system. In order to compress a gas, you need to exert energy on that gas. So it was essentially absorbed, right? Whenever you see negative energy, those are usually exothermic. So I'll have this number in joules. Joules can either be work of distance, and work can either be a measure of potential energy or it can be a measure of heat. In chemistry, we like the heat function of it, so that's why we use it. When you have these, they're usually going to be endothermic if they're positive, because the system is absorbing energy, you're increasing its energy count. If it's losing energy, so that negative, it is not negative energy, it's simply exothermic. It's losing that energy. All right? And that's the important distinction. Compressing gases usually is endothermic. If expanding gases, usually exothermic. All right. Does anybody have any questions thus far? I will take that as a no. All right. So right now I'm going to be
Well, actually, I
yes.
think was it Sophia? Do you have a problem you'd like to go over? Did you have one?
Yeah, for sure. Do you mind, Renee?
No, for sure. Yeah, you can go over them.
Okay. Okay, cool. So let me share my screen with you guys. Okay, so I have a couple of this module work problems. Do you see my screen? Cool.
Yes, we can.
So we can work some of them out. Okay, so let's do the first one. So it says 28.4 gram sample of aluminum is heated to 39.4 Celsius and then is placed in a calorimeter containing 50 grams of water. Temperature of water increases from 21 Celsius to 23 Celsius. Assuming no heat is lost, what is the specific heat of aluminum? Okay, guys, so now that Renee has talked about the formulas you need to know and stuff like that, what formula do you think you will be using for this specific problem? Any ideas?
Negative Q is equal to Q.
Okay, why?
Because we have two elements, water and aluminum.
Yeah, exactly. So yeah, you're going to be using, so the QA is equal to negative QB, right? Cool. Okay, so now let's do, okay, so what is going to go on what side? So what is going to be on your negative side, guys? It's usually your metal, right? And then your water is usually QA. So, okay, so what is my mass for my water?
50
Anyone?
grams.
Thank you. So yeah, so 50 grams, right? And then, so it's and then what is my specific heat? This one you won't probably be given it because you have to know it, or you can have it in your paper that Dr. Noveron lets you have. But what is that?
4.184.
Exactly, 4.184 grams, joules per gram Celsius, sorry. Joules per gram Celsius. Exactly, and then and then delta T, right? So delta T, so what is my difference between, okay, so we're looking at our water, right? And we know that water is increasing from 21 to 23 Celsius, right? So what is my delta T, guys? What is that difference?
2. It's a difference of 2.
2 Celsius, right? Exactly. And then that is equal to negative, right? And then your mass for aluminum is 28.4 grams, right? Of aluminum, you can see it up here. And then what is my specific heat? We don't know, right? That is what we're trying to figure out. And then so we're just gonna leave that one like there. And then finally, so it is heated to 39 point, it is heated to 39.4. So what is my difference between, so, okay, so you know how they have to both arrive to the same final temperature? So I think this problem is where on grams is heated to, I think it's heated from actually, it's not a 2. It's heated from, from 39. Okay, yeah, so 50 grams. Yeah, okay, so this should be your initial temperature of aluminum, right? This problem is worded wrong. So your initial temperature is 39.4, and then you know that in the end, they're gonna have the same final temperature, white water and your metal. So your final temperature is 23, so what would be the difference between these two guys?
16.4.
Negative.
16. Yeah, exactly, negative 16.4, right? Because it's your 23 minus your 39.4, right? Perfect. So it's negative 16.4 Celsius, right? Okay, cool.
Sorry, I have a quick question.
Yes, what's up?
Does it really matter which, I guess, which element you put after the negative? Like, or is there, like, how do you know where to put the one with the negative Q?
So, okay, so you can understand it like, okay, so the one that goes on your negative side is always the one that is going to be changing more drastically in temperature. So, you know how water has a really high specific heat capacity? So that's why, and metals usually have very low heat capacity. So that's why metals are always in your negative QB side, because those are the ones that are going to be losing the most, changing the most drastically in temperature. So that's why. So I always tell my students, always the one that with the lowest specific heat, that's the one on your negative side. Does that make sense?
Yes, yes, thank you.
And there is a difference, right? If you put like your water, if you would put on your negative, then you would end up here like with something else. So always make sure that metal's always on your negative side, okay? Okay, cool. So let's algebra this. So multiply 50 grams times 4.184 times 2. And what do you get for this side, guys?
41.632.
41 point, what, I'm sorry?
632.
632. Okay, cool. So that's good. And then we're going to have to divide, right, by all this. So divide both sides by 28.4 and negative 16.4, right? So these are going to cancel. And then over this side, over negative 28.4. And this is going to give you your specific heat, right? So do the math, and what do you guys get? And then also, I just forgot to mention this, always like see how everything is canceling out, right? So grams, you're gonna cancel them with these grams over here, Celsius with Celsius, and then you're gonna end up with joules per gram Celsius, which is what the units for specific heat are, right? So anyone figured out this number?
0.089.
0.089, perfect. Okay, so yeah, that should be your answer. And I mean, comparing it to the 4.184 for water, do you see how low the specific heat is in comparison? So yeah, always look at that. That's a great way of knowing if you did your problem right. So yeah. Okay. How many other problems do you want to do, like peer leaders? How many would you like to do? Like, would you like to do all these, or you tell me?
Wait, what happened? What was
Do you
the
want to
question?
do more?
I'm sorry. What was the question, Sophia?
Oh, do you want to do? Okay, well, actually, like to everyone, do you want to continue doing more problems for like these? Do you want to do all these 3 problems? Yeah.
Sure.
Okay, cool. Okay, cool. So the next problem. So if 40.5 joules of heat is added to a 15.4 gram sample of silver at 26 Celsius, what will be the final temperature? What will be the final temperature in Celsius? The specific heat of silver is 0.235 joules per gram Celsius. Okay, let's start. So for this one, guys, what formula are you going to be using? What formula?
Q equals ms delta T.
Exactly, right? Oh, wait, let me. Oh. Q. I'm sorry, guys. My tablet is being weird. Let me just. Okay, yeah, exactly. So we're going to be using Q equals ms delta T, right? Okay. So what is my mass? So my mass is 15.4 grams, right, of silver, always. And then my specific heat is this one, right? 0.235 joules per gram Celsius. And then finally, delta T. So I'm looking for my final temperature, right? So it's going to be TF, that's what I'm looking for, and then minus my initial temperature, which is 26 Celsius, right? So 26 Celsius. Okay, so now let's start working this all out. So first multiply these two guys, right? So what do you get? Oh shoot, and then I forgot, I forgot Q. You know your Q is 40.5 joules, right? Like I forgot to put the Q here. 40.5 joules. Okay, so now what would you guys do here first? How would you algebra this?
Multiply grams and joules per gram centimeter Celsius.
Yeah, multiply grams in your did you say your specific heat?
Yes.
Okay, yeah, so do that, right? So multiply 15.4, and let me get my calculator with you guys. So 15.4 times 0.235 times 0.235, that gives you 3.619, right? And then grams canceled with grams, so you end up with joules per Celsius, right? Cool. And then this is times TF minus 26 Celsius. And then this on this side, you have 40.5 joules, right? Okay, guys, so now what can you do? How can you isolate this, how can you isolate this number from your TF minus 26? What would you guys do?
Divide by 3.6919.
Yeah, exactly, right? Divide both sides by 3.619. So by doing that, these cancel out. And then divide it on this side, so 3.619 joules per Celsius. Okay, and so tell me, what number do you get down here?
I got 11.19.
Uh-huh.
I got 11.19.
So 11.19, right? And then our joules canceled, and now we end up with our Celsius, right? We just have Celsius right now. Cool. Okay, so now we're almost there, right? What would you just do? Now you just have to add the 26 Celsius, right? So add it on both sides, plus 26 Celsius. And what is your final temperature, guys? And this makes sense, right? Because light turns DC units. And go ahead, what were you going to say?
37.19.
37.19. Thank you, Savannah. Okay, yeah, perfect. And this should be your final answer, guys. Cool. Any questions on this? No? Perfect. Okay. Let's do the next ones. So, okay, let's see. Okay, so a gas with an initial volume of 6 liters was heated from 25 Celsius to 310 Celsius at a constant pressure of 1.5. Find the work done by the system in joules. Okay, guys, so for this equation, what do you think you're gonna use? Any ideas?
W equals negative P delta V.
Okay, yeah, so for sure we're gonna use that eventually, right? W equals negative P delta V, right? Okay, and we need to find our work, right? We need to find this pace. However, do I have enough information for my delta V? No, right? So this is when what are you gonna use then? What did you go over in module 7?
Q equals M times S.
Okay, yeah, so that is another formula, but do you think you're okay? So look at your givens, guys. You have liters and you have two temperatures, guys. So you know your initial volume, right? You have, so delta V is your V final minus your V initial. So you have your V initial, right? But you're missing your V final. So how can you get your V final? By using these two givens.
Using the Charles gas law.
Yeah, exactly. You have P1 V1 equals P2 V2. So guys, you might get problems like these too, right? You can combine so you might be using formulas that you saw in module 7 and combining them with module 8. Okay, so just be aware of that. So we're looking for our V2, right? Our V final. So let's isolate our V2. So it's gonna be, our V2 is gonna be equal to pressure 1 times volume 1 over pressure 2, right? I'm sorry, oh, you know what, I messed up. It's the temperature one, not the pressure one. So it is P1 over T1, right? Equals P2 over T2. Does that make sense? Did I
V1
look
over
good?
V1 over T1 and V2 over T2?
Oh shoot. I'm sorry. Yeah, it's V1 over T1. And yeah, that. Thank you. Okay, yeah, but you know what I meant. We're using gas laws formulas, guys. Okay, yeah, so we're looking for our V final, right, our V2. So V2 is gonna be equal to V1 times T2 over T1, right? Okay, so let's figure all of this out. So our volume initial is 6 liters. And then what do I have to do to my Celsius, guys?
Convert that to Kelvin.
Kelvin, right? Exactly. So my temperature final, my T2 is 310 Celsius. So 310 plus what? Plus 273, right? So 310 plus 273, that gives me what, guys? How many Kelvin?
583.
Yeah, exactly, 583 Kelvin, right? Perfect. And then divided by my initial temperature, which is 25. So 25 plus 273, that's 298 Kelvin, right? Cool. Okay. Okay, so figure that out. What is your final volume?
$11.74.
Yes, it's 11. Okay, so 11.74, correct. 11.74, and then always your units, remember, liters. Right? Okay, so now that we have our final volume, now we can go ahead and plug it up here, right? So let's find our work. So work is going to be equal to my negative pressure. So what is my pressure, guys, for this problem?
1.5.
1.5 atmosphere, right? So 1.5 atmospheres, and then times delta V. So we figured out my volume, my final volume is 11.74, right? 11.74 liters minus my initial volume, which is 6 liters, right? Okay, and then, so let's figure this all out. So 11.74 minus 6, that's 5.74, and then multiplied by my atmosphere, so times 1.5, that's 8.61 liters atmospheres, right? Okay, so, oh, and then it's gonna be negative. So negative, wait, final 11.74 minus 6, 12 times negative 1.5. Yeah, okay, so it's gonna be negative 8.61 liters, right? Are you all with me? Okay, cool. So is this my final answer, guys, or do I still have to do something else?
You convert it to joules.
We're going to convert it to joules, right? And what are you going to use for that? What is your equivalence of joules and liters atmospheres?
1 liter atmosphere is equal to 101.325.
So yeah, okay, exactly. So 1 liter, and you know what? I don't know why I mess up with this. Yeah, okay, yeah. So it's 1 liter atmosphere. Wait, let me just make sure. Okay. Yeah, okay, yeah, I'm sorry. Yeah, so 1 liter atmosphere is equal to 101.325 joules, right? Okay, cool. So now multiply those two, and what is your work, guys? What is your answer? And again, like Renee mentioned right now, always like it's a great idea to use dimensional analysis because you see how everything cancels out perfectly, so you don't have to like be like, oh, what was the unit? So yeah. So that times 101.325, that gives you what? What are my joules? It's a big number.
Negative 872.4 joules.
Exactly, negative 872.4, right? And then joules. Cool. Perfect.
I have one more question. Sorry.
Go ahead.
So they had just mentioned that for the gas laws, we didn't have to convert like either to liters or to Kelvin or anything, but I noticed that we converted in this case to Kelvin. Is there any reason why we have to do that? Or could we?
Well, so someone want to jump in? My understanding is that you don't have to convert. Like if you have milliliters, you don't have to convert to liters. But I believe temperature you always convert it to.
Okay.
Temperature you always convert it to Kelvin. But I don't know if anyone else has another pure liter might know.
Well, in regards to I just say for module 7, yeah, you always, yeah, because it does get it does change from module to module. So module 7 for sure, when you're doing anything with those equations, your temperature is preferred in Kelvin. But when you're doing module 8 equations, the magnitude of difference between, like if you do it's because when you do subtraction of like kelvins and then Celsius, they're the same thing. That's why in that module we don't convert it. But yeah, in module 7, do keep anything that relates to module 7, keep it in Kelvin, and then anything in 8, it doesn't really matter. You just gotta focus on what you're asking for, on what they're asking you for. Because I think in your homework, maybe, because I know there was one like last semester. If let's say there's a module 8 problem and they ask you for temperature in Kelvin, well then you would switch it to Kelvin, right? But the math is the same as what module 8 is saying, but just in simple terms, yeah, for sure, change it to Kelvin from in module 7 stuff, and in module 8 stuff, you can keep it as Celsius.
It's good to stay on the safe side.
I'm gonna elaborate on what Andre just said. So yes, for module 7, you use Kelvin because when you're working with gas laws, you have to use Kelvin for your temperature. Like that's a must. So for example, in this problem, yes, it's a module 8 problem. However, we used a gas law, like a gas law rule, right? So that's why we converted it to Kelvin. But and in this problem, you see, we don't involve like Celsius. Like for example, in the Q equals ms delta T, we have to use Celsius because like it is part of our, like in this equation, it is part of it, right? Like your temperature here is in Celsius and your specific heat is joules per gram Celsius, right? But you see that this work formula, the negative pressure times delta volume, you don't really use Celsius, if that makes sense. So that's why, since we were using a gas law equation on this problem specifically to figure out our volume too, that's why we converted it to Kelvin. I don't know, does that clear up your question?
Yes, it does. Thank you so much.
Perfect. Okay, and I think Karina was gonna say something.
I already said what I did. You guys can convert if you want to stay on the safe side, but you guys can also you guys can follow Andre and Sophia's advice. I just kind of wanted to say that.
Okay, perfect. Okay, guys, so let's do one more problem. So can someone read this for us? Oh, wait, no, that's what I tell my students, I'll read it. How many kilojoules of energy are needed to raise the temperature of 165 moles of water from 10.55 Celsius to 47.32 Celsius? Okay, guys, so what equation do you think we need to use in this problem? So kilojoules are involved, moles are involved, and then we have temperature involved. Any ideas?
Would it be Q is equal to ms delta T?
Yeah, so we are going to use Q equals ms delta T, right? So we do have mass in some form. It's in moles, right? So we're going to have to convert it to grams, right? And thank God we know what molecule we're working with. We're working with water, right? So let's convert 165 moles of water to grams. So 165 moles of H2O. How many grams of H2O are in 1 mole of H2O?
18.
18, right? 18 grams of H2O. Cool. So multiply 165 by 18, and what is your answer?
2970.
2970. So we have 2,970 grams of H2O, right? Cool. And then what is my specific heat of water, guys? This by heart, you know this.
184 joules
4.8
per gram Celsius.
Yes, centimeters, just kidding. Yeah. Joules per gram Celsius, right? Joules per gram Celsius. And then finally, your delta T. So delta T, it is in Celsius, right? That's what we were mentioning right now. So 47.32 minus 10.55. What is your answer for that?
$36.77.
Exactly, 36.77 Celsius, right? Cool. So now that you have everything, combine, multiply it and see how everything cancels out, grams with grams, Celsius with Celsius, and then you end up with joules, right? Cool. So multiply everything out, guys. What do you guys get?
Um, 457,075.51.
Okay, 4,560. Okay,
Oh, my
let me
bad.
do it one more time. Okay, wait. Is it 4,56921?
I got 457,075.
Okay, let me try one more time then. Okay, 2970 times 4.184 times 36.
Oh, I see what I did wrong. I multiplied it by 2,971 instead of 2,970.
Oh, okay, okay. Okay, they were pretty close anyways. Okay, yeah, so 4,56921. So 456,921.67 joules, right? And then is that it, or am I missing a step?
You convert to kilojoules.
Exactly. Always read your problems right. You're converting to kilojoules. So kilojoules to joules. So you know that in one kilojoule there are 1,000 joules. So divide by 1,000, or you can also move your decimal point 3 times to your left. So your energy in kilojoules should be 456.921 kilojoules. This should be your answer. Okay. Any questions, guys? Perfect. So that is all the problems I have on this module. I don't know if anyone else has other questions regarding module 8. Speak up now. No? Okay, cool. Okay, well, thank you guys. I'll pass on to module 9 then.
Oh, just real quick, Kaylee, do you still want to go over your module 8 problems, or do you think, or is there anything that you feel like you want to cover, or do you think module 9 would be the best?
I think it's really up to what the students want. If they want to keep working on some of those like work calorimetry problems, I have a couple that we could go over, but I know personally my students, when I just had them in workshop like an hour ago, they were more concerned with the thermochemistry problems. So if that's what the majority here wants to go over, we might want to move on to 9 with the last 45 minutes. It's I guess just take a poll.
Yeah, or the students, yeah, you do what do you guys want? Well, yeah, yes, so yes, module 9, or yes, module 8, Francisco.
9, please.
Real quick before we go to 9, I actually found in the workbook, hopefully
A resounding 9.
I think it was, who was it that asked that question? I think it was Marcela that asked the question about, or I don't know, I forgot who asked it, but that question about changing Kelvin or why we change it. There's a good paragraph on page 197 where you see the little, I forgot what that's called, the asterisk, I think, where it says note. I recommend reading that paragraph, okay? Because that explains it into, and you can have that definition all the time. If you didn't get from what we said, yeah, page 197 on module 8, page 197, the little paragraph where it says note, where it starts note, and then that's where they explain that question, that why do we not change it in module 8 from Kelvin to Celsius, okay? Just wanted to state that real quick, but yeah, let's move on to module 9 then. So yeah, Kaylee, if you have any problems that you like to go over, go for it. I know Corina has some too, so so we'll try to divide them up. Okay, so yeah, go for it though.
Alrighty, sounds good. Give me just a second. I'll share my screen and we can. Okay. All right, so we have the problem on the screen. Calcium carbonate and sulfuric acid react to yield calcium sulfate, water vapor, and carbon dioxide. Determine the enthalpy of formation of calcium sulfate given the following values. And then we're given all of the enthalpy of formations for the reaction plus all of the variables and compounds within the reaction. So somebody tell me, how do y'all think we should start this problem?
We should start it by writing out the equation in its elemental form.
Perfect. Okay, so how would we do that?
Oh, shoot. Calcium carbonate, that's CaCO2, right?
Yeah, okay, so you're really close. So this is what I like to do. So we have calcium, so we know calcium Ca, right? What's our charge for calcium?
Positive.
Okay, positive what?
Oh, positive 2.
Positive 2, perfect. And then carbonate, what's our compound for that polyatomic oxoanion? Remember our rule of 7.
CO2, right?
Okay, you're really right on the CO part, but remember it's 8. It ends in ATE, so that means that it's going to have its normal amount of oxygens.
Okay.
So that means if it's on the outside of the 7, how many oxygens does it have?
3.
3, perfect. And then what would be the charge for carbonate?
Negative 2.
Negative 2, perfect. Yeah, and so if we know it's negative 2 and calcium's positive 2, those charges will cancel each other out. So when we write out calcium carbonate, it'll just be CaCO3. Okay. And then the next thing we're told is that calcium carbonate is added with sulfuric acid. So what would be our sulfuric acid compound formula?
Okay. H2SO4.
Perfect. Thank you, Victoria. Yeah, guys, if y'all wouldn't mind like shouting out answers without typing them into the chat, because I can't see the chat when I'm like this. And so we know that those are our 2 reactants, and we're told that it's yielding calcium sulfate. So what is calcium sulfate going to look like?
CaSO4.
CaSO4, perfect. And then we also know that it's going to give us water vapor and carbon dioxide. Okay, so now that we have our complete reaction, what would be the next step?
Balancing out the equation.
Yeah, exactly. We have to check to see if it's balanced, and if it's not balanced, we need to balance it. So take a second and let me know if this looks balanced, and if it doesn't, where should we add our coefficients?
It looks balanced.
Okay. Does anybody disagree with Sebastian? Or agree with Sebastian? Give him that boost.
I agree.
Okay, awesome. Yeah, so we've got 2 that agree, and I would also have to say that it does look balanced. So that's awesome. So what would be the next thing that we should proceed to do here? Actually, let me ask y'all this. When we're dealing with the enthalpy problems from Module 9, We know that we're looking at our like enthalpy of change for the reactions, because remember our delta sign means change of something. So what is going to be like our kind of our mantra for module 9? What are we subtracting? What do we need to remember? Like remember for module 8 with work, we did our delta volume, right? So we did our final volume minus our initial volume. So what's that similar situation happening in module 9?
Different heats.
Yeah, we're looking at our different heats, and those come from what makes up our reactions, right? Our reactants and our products. So for module 9, what we really want to remember is that it's going to be the sum of our products, right? The sum of our products minus the sum of our reactants. And that sigma sign is just our sum sign, right? The sum. So that just means when we're given this laundry list of delta H's, all of these enthalpy values, right, for all of our reactants and our products, that just means that we're going to have to add all of those up together for our product values, add all of those up together for our reactant values, and then subtract them from each other. And we want to remember, though, that it's always final minus initial. Same thing here. Final is our products, initial was our reactants. So we want to remember that it has to go in that order. Because I would believe if you flip it, there might be an answer choice that is that flipped version of it. Okay, so if we keep that in mind, our products minus our reactants, I would say a great next step is to write out what you're given, just to make sure that as you plug this all into that equation that you don't make any mistakes. So if we just start with what we're given, our H, Rxn, that just means that that's the enthalpy change of the entire reaction. Okay, so that would be what all of the enthalpy changes equal when we do our products minus our reactants. So that value ended up being 49.8 kilojoules per mole. And then our calcium carbonate value ended up being negative 1206.9 kilojoules per mole. Our sulfuric acid value, was negative 811.3. And then our water was negative 241.8. Water. And then our final one was for CO2, and that was negative 393.5. So it's really helpful to write out what you're given, just because now we can see that there's like so much that we're about to be dealing with. And once we plug it all in, it's a pretty simple process of solving, but we have to make sure that we keep all of this information as organized as possible so that we don't mess up where we're plugging in our information. Okay, so if we know that we're gonna have to start with this equation, the delta H reaction equals the sum of our products minus the sum of our reactants. Sorry guys, my dog. What would be the first thing we want to use here? Which one of these values would be the first thing we want to plug in?
Negative 49.8.
Okay, right, the negative 49.8. And why would that be the first one we want to use?
Because it's delta HRXN?
Yeah, because it's it's the equivalence of where our entire reaction is going to end up. Okay, so then from there, we'll do a little bracket because we're going to do a long equation. And so we're going to start, remember, with our products. So what would be the first thing we want to add in here?
Negative 811.3.
Okay, because that's our value for, nope, that's our value for our sulfuric acid.
So negative 241.8?
Right. Yeah, so the first, I just like to go and list in the list of what our products are. So we start with our calcium sulfate. We don't have a value for calcium sulfate because that's what we're solving for, right? So we could just start by plugging in that particular name of that ion. So then from there, we're going to add the enthalpy for water. So what was the enthalpy for water?
Negative 241.8.
Thank you. Yep. And then we're going to add the enthalpy for CO2.
Negative 393.5.
Perfect. Okay. And then all of that is going to get subtracted from our reactants. So the first reactant we have was calcium carbonate. So what was the enthalpy for calcium carbonate?
Negative 1206.9.
Perfect. And then that's going to be added to the enthalpy of sulfuric acid. And that one was negative 811.3.
Yes.
Perfect. So now from here, sometimes it's the easiest to add these up in like sections just because there's so much that you're adding. So I would add up your negative 241, your enthalpy of changes for your H2O and your carbon dioxide, and then your enthalpy of changes for your reactants. Then subtract those, and then we'll see what we get from there. So let's do. So what did y'all get?
I got 1382.9.
Did anybody get anything different or the same?
I got the same.
Perfect. So 1382.9. So then what do we need to do to isolate our calcium sulfate from here?
Divide 1382.9 on both sides.
You're close, but we're not multiplying. We're actually just adding it. So we don't necessarily need to divide. We just need to subtract we just need to subtract our 1382.9 from both sides. So that'll give us what for calcium sulfate?
Negative 1432.7.
Perfect. And so that would be your enthalpy of formation for calcium sulfate in this reaction. And if you have time on the exam and you want to double check, you could plug it in, solve for all of that again, and that should give you negative 49.8. So questions? Cool. Karina, did you want to go over a Module 9 problem as well?
I was gonna go over indirect method, so but I want to see if you guys feel confident in direct method. What do you guys think? You guys feeling confident?
I feel pretty confident with this.
Anybody else? Everybody agree, or are you guys gonna let Paola and Sebastian speak for you?
I agree. I'm comfortable with it.
All right. Okay. I like to go over indirect method because I think it's a very for a lot of people, it's very hard. How many of you guys think indirect method seems a little bit hard?
It's a little tricky.
A little tricky. It actually does take a little bit of, it takes a bit of practice. That's mostly what it takes. And it does seem very intimidating at first, but I promise you it's actually really not that bad. Okay, so let's go ahead. I'm gonna go ahead and let me find out. All right, there we go. There's a problem. Okay, so let me show. Share my screen. You guys, if there are any of my students oh my gosh. Okay, I was gonna open up that. If there are any of my students here, and I know there's at least I think one of you guys might be familiar with this PowerPoint already. I really like this one mostly because it has plenty of problems to practice. So let's go ahead and try this one. 2 messages in the chat. Okay. All right. So calculate the standard enthalpy change for the reaction. 2 aluminum plus Fe2O3 yields 2 Fe solid plus a Al2O3 solid. Given the following reactions. Okay, so we have these reactions, and what we want to do basically is that we want to rearrange these equations in such a way that we have, for example, here we have aluminum and what is this, guys? Aluminum and what is this? Anybody tell me what's
iron oxide?
Which one?
Oh, shoot. Iron 2 oxide?
Not quite there. You're close, but you're close.
Iron 3 oxide?
All right. You guys sure it's iron 3 oxide?
Yep, it's iron 3 oxide.
Yeah, it is iron 3 oxide. So just remember what's the charge on oxygen?
-2.
-2, right? So remember, this is an ionic compound. So what does that mean?
It's a metal and a
not metal.
Non-metal, right? So if you have a metal and a non-metal, what are you doing with those? Are charged, right? They're ions. So how do you write the formula? What do you do? I'm giving you guys a hint. If you guys can see,
crisscross.
Crisscross, right? So what are you crisscrossing?
The 3 and the 2.
3 and the 2, right? So iron is gonna be +3, so that's why it's gonna be Fe2O3. So it's iron 3 oxide, right? Okay, so we have aluminum and iron 3 oxide on the reactant side, on the left side, reactants. And then we have iron and, what is the name of this one? What's the name of this one?
Aluminum.
Aluminum 3 oxide.
It's not the 3. There's no 3 in this one because aluminum, the difference between iron and aluminum is that aluminum is a main group element. So those don't have Roman numerals to differentiate. I think only lead has them, but aluminum doesn't need one. Doesn't have a Roman numeral to differentiate because it only goes to +3.
So would it be aluminum oxide then?
Yeah, it's aluminum
No
oxide.
more rules.
Yeah, no rules for aluminum. No, that rule doesn't apply to aluminum. I think it does apply to lead, but yeah, I think it does. Yeah, so what we want to do is rearrange these equations in such a way that First of all, we have the reactants, so aluminum and iron trioxide on the reactant side, and we have iron and aluminum oxide on the product side. This also means that we're going to be able to get rid of some compounds that aren't in I like to call this the target equation, because this is what we want. This is our target. This is our objective when we're rearranging. This is what we want to have in the end. After rearranging and manipulating, multiplying, and have cancel out stuff. Okay, so let's look at this one first. So do we have aluminum on the correct side that we want?
Yes.
Right? Do we have the same amount?
Yes.
Okay, so we're good with aluminum. Do we have oxygen in the final equation, in the target equation?
We don't have oxygen.
We don't have it, right? What about aluminum oxide?
Yes, it's there. It's on the right side as well.
So on the right side and right amount?
Yes.
All right. Okay, so we're good. You guys think so what do you guys think? Do we need to change this one?
Keep it as is.
Keep it as is? All right. So we're going to keep this as it is. All right, let's look at the next equation. So we have iron right over here. What do you guys think? Is iron on the right side?
We need to flip it.
We need to flip it. Do we have the right amount?
Yes.
Okay, so we don't need to multiply or anything. You just need to flip it. So how do we flip it?
Multiply the whole thing by -1.
Like -1. It just means that it's going to flip the whole equation. All right. So we can rewrite this equation for comfort's sake. Oops. Oh, my bad. That's the wrong one. So how should our equation look like? I'm not gonna write it out yet. How should our flipped equation look like?
It should look like Fe2O3 yields to 2Fe plus 3/2 O2.
2FeS plus 3/2 O2. Yes. Okay. So what happens to this number?
It gets turned into a positive.
Gets turned into a positive, right? Because you're multiplying by -1. So negative and negative gives you positive, right? So let me go ahead. We can also rewrite that. So delta H, positive 822.2 kilojoules per mole. And just for convenience sake, just to make sure, just for convenience sake, we're gonna rewrite the one on the top, so we don't get lost. L2O3S. Okay, we rewrote the second one, right? Okay, so we have everything we have everything where we want it to be, right? Okay, so, but notice how we still have these oxygens here. What are we gonna do with these oxygens?
They cancel each other out.
You cancel each other out, why?
Because they're on opposite sides and they're equal to each other.
Right, exactly. Savannah, you're on fire today. Awesome. So we can cancel these out. We've gotten rid of our oxygens because there's no oxygens in the target equation. So how do we write our final equation then?
2ALS plus Fe2O3S yields Al2O2S plus 2FeS.
All right. So that's our equation. That's how we make sure that we did everything right. If we got this same equation, obviously this is rearranged, but it's the same products. Now in this case, the order doesn't really matter as long as you guys got the right equation, the right products, and the right side, everything. Okay, are we done here?
No.
No, what's missing, guys?
Have to add those two together.
Yeah, we're gonna add the enthalpies. Obviously, this should be positive. Just remember to put into effect whatever manipulation you did, like flipping it or multiplying anything. Just make sure you got that. Okay, so who can tell me what our enthalpy is?
Negative 847.6.
847.6 kilojoules per mole. Right, everybody, y'all got the same answer, Savannah, or?
Yeah, I got the same one.
Right. Okay, so how does everyone feel about this problem? Feel good? Easy peasy, right? So far. Okay. You guys want to do one more? A little bit difficult. A bit of extra spice on these. These have some animations for convenience also, but let's just, I would prefer if we went through this together, like this. All right, so here's another one. Calculate the standard enthalpy of formation of acetylene, C2H2, from its elements. So I have 2C graphite. By the way, over here is a typo. There should be just gas. This should be just G, not graphite. My bad. From its elements, 2C graphite plus H2 gas yields C2H2. All right. So actually, I'm gonna have you guys pick first. How about you guys pick first? Which one do you guys want to look? Which equation do you guys want to look at first? You guys can pick whichever one you guys want. You don't really have to go in order. Whichever one you guys feel best with.
Let's go with the second equation.
Second equation. All right. Okay. Okay. So what do we do? So we have H2 gas and plus 1/2 O2 gas yields H2O. Okay. So we have H2 in our equation. H2 in this equation. Are they the same? Same amount?
Yes, they're the same amount.
Same amount? Same side?
On the same side, yes.
All right. What do you guys think? Do we need to manipulate it?
No.
Okay, we leave it as this. All right. We leave it as this. Which one do you...
Can you explain the part again, please?
Sorry?
Can you explain again the part? The part that we have to see we have the same elements.
Yeah,
please.
sure. So when we're doing in indirect method, what we want is that we want these parts, like we want the reactants and the products to be moved to the same side. So we want reactants on the left side. So we want carbon graphite on the left side. We want H2 on the left side. So we're gonna move. So wherever they are in these equations, we want to have them on this, for example, H2. Here it's on the left side, on the reactant side, and here it's on the reactant side as well. That's where we want it. We're not gonna flip it. Does that make sense?
Yes, thank you.
Yeah. So what we're gonna do is we want to have the same amount. So for example, we want to have 2 carbons. We want to have 1 H2, both on the left side. And then we want 1 C2H2 on the right side. Okay? Everybody good?
Yes, thank you.
Yeah, no problem. I tend to repeat myself a little bit. So, okay. So we already decided that this one, we're not going to change it because we already have H2, the same amount, 1 H2, which we want, on the reactant side, which we also want. So this one's already good. Which one do you guys want to look at? The first one or the third one? You guys can pick.
The third one?
Third one. All right. So you have 2 C2H2 plus 5O2 gas yields 4 CO2 plus 2 H2O liquid. Okay. So what is in here that we want on our target equation? The one that we want, the equation that we want in the end. This equation.
C2H2.
You have C2H2 here, right? Do we have the same amount?
No,
Is it on the same side?
it is not on the same side.
All right. Okay. So what are we gonna do about it? Cry. Joke. Just kidding.
Oh, you need to flip it and then multiply it by 1/2?
Yeah. So flip it. So to flip it, we use a negative sign, right? Then we multiply by 1/2. Okay. So let's go ahead and rewrite that. Let's write our equations that we have so far. 2O2 gas yields H2O liquid. So the third one, how do we rewrite it? We multiply by 1/2, negative 1/2. So how do we rewrite it?
Two CO2 plus H2O yields C2H2 plus 5/2 O2.
All right. There's 5/2 O2, right? Yes. All right. Okay. So let's look at our remaining one. So we got this. We're done with this one. Let's look at this one. This is the last one that we have. Okay. What's in our target equation? What do we have here that's in our target equation?
We have carbon.
Carbon, right? We have C, graphite. Do we have the same amount?
No.
Do we have it on the same side that we want?
Yes.
All right. So what are we going to do about it, guys?
Multiply times 2.
Multiply times 2. Okay. So I multiply everything times 2. How do we rewrite it?
Two C plus 2O2 yields to 2CO2.
2O2 yields to CO2. All right. And actually, let's go ahead and write the enthalpies so we don't get lost. So delta H, we multiply times 2. What is that? What's delta H now?
Negative 787.
787. What about for the second one? Again,
It stays the same.
stays the same. What about for the third one?
That turns into 1299.4.
1299.4. Positive, right? Okay. Joules. Yeah, positive, right? Because there's a negative. Okay. So, what can we do with? Is there anything here that we can cancel out?
We can cancel out H2O.
H2O. Cancel out H2O.
Cancel out CO2.
Cancel out CO2. CO2 is gone.
And then we can, oh, sorry.
Keep going, keep going.
Okay, and then we can also cancel out O2.
O2, right. Okay, so I want you guys to notice something. I don't know if you guys have already noticed, but what do we, which O2 do we cancel out here on this side?
Both of them.
Both of them, right? You guys understand why? Everybody understands why?
Isn't it because you add 2 plus 1/2 is equal to like 2.5, which is the same as 5/2?
Right, exactly. So you just add these together. You can change, see this fraction? You guys, this whole number, I think you guys might remember from, I don't know, elementary, middle school, math. You can change this into a fraction. So 2 changes into 4/2 plus 1/2 equals 5/2. Right, just, okay. So put these two together, cancels out, cancels out, cancels out. All right. And we are left with these 3. And what do we rewrite? What is our final equation?
The final equation is 2C plus H2, oh yeah, 2C graphite plus H2 gas yields to C2H2 gas.
All right. So we got the equation that we wanted. We made sure that that's what we got. Okay. So what's the enthalpy, guys? That's the enthalpy. It's on the bottom in white because I just ran out of space.
226.6.
326?
226.6.
226.6 positive, right?
Yes.
0.6 joules per mole. All right, everybody agree with that answer? Everybody got it? Or did anybody get a different answer?
I got that answer.
All right. Okie dokie. How's everybody feeling with indirect method? Feeling more confident? Okay, we have a few more minutes left. I don't know if there's anything else you guys might want to look at. You guys want one more indirect method problem? Do you guys want any other questions?
Did we get a problem like from problem 6 on module 9?
Problem 6. I think we can do something. I think we can do that that one. Kaylee, do you have any questions similar to that? By chance?
I think so. Give me just a second. Oh, yeah, I do.
All right, but
Okay, so I have one that asks the same thing. It was just using different numbers. So we're given carbon in a solid plus O2 as a gas yields CO2 as a gas. And we're asked to calculate the heat change in kilojoules when we are given, we're given nanograms. So that's weird, right? So CO2 equals 8.7395 times 10 to the 2 nanograms. And then the delta HF was equal to negative 395, or 393, sorry, 0.5 kilojoules per mole for just for the reaction. Okay, so the first thing we're going to want to do is convert these nanograms. What do y'all think we should convert them to?
Convert them to grams?
Okay, yeah, that's a great first place to go, to convert them to grams. And then from grams, where should we go?
Moles.
Yep, to moles. So that's our game plan there, right? So this takes us back to some of our earlier modules of 8.7395 times 10 to the second nanograms. So does anybody remember how many nanograms are in 1 gram?
Times 10 to the power of 9.
Yeah, perfect. So 10 to the power of 9 nanograms are in 1 gram. Okay. And then from grams, we're going to moles. So what do we need in order to convert our nanograms or our grams of CO2 now into moles?
The molar mass of CO2.
Okay, awesome, perfect. So what is our molar mass of CO2?
$44.
Awesome. So now when we get rid of what we're trying to cancel, we're left with just moles of CO2. So when we multiply and divide, what do we end up with for our moles of CO2?
I'm not entirely sure how right this is, right? But I got 1.986 times 10 to the 10th.
I got something very similar, but not 1.98. My decimal was in a different place.
I got 1.98 times 10 to the negative 8.
I'm getting 198.625. And y'all are getting 1.98?
Mm-hmm.
So we divide 8.735 times 10 to the 12th by 10.
Is it 12 or 2?
Oh, it's 12, sorry, or that's why. Okay, yep, my bad. My apologies. Yeah, so 1.98 or 198.62 moles of CO2. And then from here, really all we have to remember again is our mantra for Module 9, which is products minus reactants. Okay, so what we would be left to do then is is to use our kilojoule per mole value that we have, and that'll help us solve for our kilojoules, right? Because we have our negative 393.5 kilojoules over 1 mole, right? Was our enthalpy. Sorry, not products minus reactants. Ignore what I said up here. Yeah, so we have our kilojoules per mole of our enthalpy of formation for CO2. And now we have our moles of CO2. So really all we need to do is multiply by our moles that we just found. And that should give us the kilojoules that we're looking for. So what did y'all get?
I got negative 78, 156.97.
Perfect. And then if we cancel out our moles, that tells us that we're left with our kilojoules, which is what we were asked to leave our final answer in. And I think the only difference with the number 6 on module 9 was just that it was phosphorus pentachloride instead of CO2, but the process should be exactly the same.
Okay.
Is there any questions?
No. I have a question regarding the recording. Where can we watch it? Like tomorrow in the morning or tonight, later tonight?
So it'll be posted onto the Peer Leader YouTube channel, which was linked in the chat earlier, and we can definitely pull that link up again. And once it's posted on there, if you're following the YouTube channel, you'll see it. If not, maybe your peer leader will be able to post it on Blackboard.
I saw it. Thank you. Yeah.
I have a question for the problems that are like this, but in the homework that is due today.
Okay, what module? Was it module 9 that you had due today?
It's Thermodynamics.
The lecture homework.
Yeah.
Okay. Could you go ahead and read that question out loud?
It says, given the thermochemical equation 2SO2 plus O2 yields 2SO3 delta H neg.
Could you slow down? Could you start over again? Sorry, 2SO2?
Yeah, 2SO2 plus O2 yields 2SO3.
Would you be so kind to include the states as well?
Delta H is negative 185.2.
Delta H equals negative 5?
No, negative 185. 185.2 kilojoules over mole.
Kilojoules per mole. Okay. Is that the whole question?
Calculate the heat evolved when 50.9 grams of SO2.
When 50.9.
0.9. grams
of SO2. 2.
Is converted to SO3.
Converted to SO3. Is this the whole question?
Yeah.
Okay. Does it say if oxygen is in excess?
No.
I guess we can assume it's in excess. Okay. Okay. So you guys remember module 4? What was module 4 about? You guys remember?
Stoichiometry.
Stoichiometry. What else? I think it was either 4 or 5. I can't remember which one it was, but you guys remember your limiting reagents? Those limiting reagents problems that everybody complained about because they were tedious. All right. So in this one, what you guys want to do is that you guys want to calculate the heat of this reaction that occurs with the formation. This is the formation, the heat of formation of SO3. So, but we're given the grams of SO2. So, what do we do with this? You guys remember when we had to calculate how much product we got in those after those limiting reagent problems? So that's basically what we need to do here. What we want to do is that based on how much of our reactant there is, obviously we are going to assume that O2. We're going to assume that O2 is in excess, and we're going to convert from our product, reactant. This is our reactant to our product. So how do we find out how much product was made? Anybody remember how to do that? Any ideas? With the oxidizing agent, no. In this problem, we don't need to find out what the oxidizing reagent, but we do need to find out how can we calculate the product, how much product we have based on how much reactant we have.
Is it with molar masses and trying to see which one is the limiting reagent that way?
No, we already, first, yeah, we can find out what the limiting reagent is, but so if we have excess O2, what is our limiting reagent?
SO2?
SO2. So SO2 is going to be our limiting reagent. Reagent. So we always calculate. Sorry. Oh, that's fine, Paola. Yeah, we calculate with the limiting. We calculate how much product we got with the limiting reagent. So we already know what our limiting reagent is, how much mass of reactant we have. How do we go from reactant to product? Actually, what's the first thing that we should do? Should we be using grams?
Moles?
Moles, right? We should use moles instead. It's a lot easier. Okay, so 50.9 grams of SO2. Okay, we want to go from grams to moles. What goes on the top, what goes on the bottom?
And moles on top, grams on bottom.
Moles on the top, grams on the bottom. All right, SO2. We're gonna clarify that this is SO2. Okay, for every 1 mole, for every 1 mole of SO2, how many grams of SO2?
64.06.
64.06 grams. All right. How many moles of SO2 do we have?
2.
2 moles?
2.
Okay, we have. Okay, so we have 50.9 grams of SO2, right? And remember that on the top we multiply and divide with whatever's on the bottom.
0.794.
0.794. Okay, moles of SO2. Right. Right. Now we've got moles of SO2, we can try to find out how many moles of SO3 we have, how many moles of our product we have. So we use a nifty little thing that actually Sebastian mentioned earlier, so I hope you guys remember what that word was. What was it? What do we use? Starts.
Molar mass.
What was it?
Molar mass.
Not quite yet. Something else. Mole to mole ratio, which is also called
stoichiometry.
Stoichiometry, right? Stoichiometry. I see that, like that face is like, oh, I had it. All right. Okay, so it is mole to mole ratio or stoichiometry. Okay, so we're going from moles of SO2 to moles of
SO3.
SO3. So for how many moles of SO3?
2.
2. Okay, so we have 2 moles in the equation. For every 2 moles of SO3, how many moles of SO2? Which we want 2. 2 moles. So essentially we're gonna have a 1-to-1 ratio right there, because 2 over 2 is just 1, so it's the same thing as 1-to-1 ratio. So 2-to-2 ratio, I guess you could say that. Okay, so how many moles of SO3 do we have then?
0.794 moles.
0.794 moles. Okay, 0.794 moles SO3. Right. Okay, yeah. This is the amount of moles that we get for SO3. Right. Okay. So now that we have moles of SO3, let's go back to what the problem was asking us. It says, calculate the heat evolved, so enthalpy, in other words, the enthalpy, the heat, the energy, when 50.9 grams of SO2 is converted to SO3. So remember, what did we say this was? This is the heat. This is known as the heat of formation. For what? For what?
The products or reactant.
For the product. For the product, right? For SO3. In this case, for SO3, this is the enthalpy, or the heat that evolves. The kilojoules produce the heat that evolves for each mole of SO3, of product of SO3. Make sense? Okay. So then, how can we calculate how much heat evolved from this amount of product that we have here in the bottom?
Multiply it by the moles.
Right. Multiply what? Wait, what? Multiply what by the moles?
Multiply the heat of formation by the moles.
Bingo! Exactly. Right. So the heat is going to be 1.8, 5.2 kilojoules per mole. I'm putting in the units because that's important. It's going to be important. Times 0.794 moles, right? Okay, look at the units. What can we cancel out?
Moles.
Moles, right? Because it's kilojoules per mole or kilojoules over mole. We can cancel out moles and we're left with
Negative 147.05.
negative 47?
147.
147.05.
05.
05 kilojoules. And that, my friends, is the final answer. Okay, does everybody understand how we got to this point? Okay, in summary, what we did, okay, first thing that we did, just to recap, I'm glad that helped you, Paola and Victoria. So first thing that we did, make sure that we got moles of product. Well, more like we got 1 grams to moles of reactant, moles of reactant to moles of product. And finally, the heat was, well, the heat was equal to the delta H, the reaction, times moles of product. Because this is the heat of formation of SO3. Okay. All right. So do you guys have any other questions, concerns, complaints?
Yes. The exam, would it focus on more so on one of the modules, or is it an equal focus on all three, or?
So we don't see the exams, first of all. So we are not, we don't really know how much, but it should be about an equal emphasis on all of them, especially because it's only gas laws, thermochemistry, and enthalpy. Calorimetry and enthalpy, mostly, that's it. And ideal gas laws. So you guys should at least be, maybe instead of focusing more on like what might be heavily emphasized on the exam, in this case, try to focus on what you guys think maybe is probably you guys maybe aren't that great at yet, so that you guys can improve on that and you guys feel a bit more prepared for the exam. And that's why we have these reviews, so we can help you guys with whatever you guys may feel weak with, or
not. I had the same question, but just different number. I had like 150.2. So it looks like it just, everything is the same other than the heat of formation. So I multiplied the 0.794 to 150.2. I got a different answer from the one I answered before. So that's the only thing that I have a problem with. I don't know if the thing, it said it was right when I turned it in. So I don't know, I did it wrong, or so, the question is wrong.
You're saying that the one thing that changes is the enthalpy of formation, this?
Yes.
So I think if you have, as long as you more or less, you basically follow the same thing, like the same process we did, like finding out going from grams to moles of the reactant, and then from the moles of reactant to the product. And then you multiply by whatever your enthalpy is times your moles of the product. I think that you should be all right. I think it might have been a case of just changing the numbers. Dr. Noveron kind of likes that,
yeah. Just confused of the things. I don't think I'm doing the right thing then. Because like that's why I did the entire thing, and I'm just not getting the same answer as I was getting.
So if for example this number, like the delta H that you're given is different, then that should definitely give you a different answer. Because this one takes into account the fact that this is the number that you're given. So if this is if you're given enthalpy, if your delta H is different, then that would give you a very different answer from this.
Oh yes, for sure. But I know that the 0.794 is the same because the same formula was there. It's the same formula, and the only change was the. Oh, okay. Now I get it. I guess I didn't. I guess I have a different grams, so that's why I won't get it. Okay.
That could be that too.
I was like looking at it.
Could be that too, because this, if the grams change, then the answer is also going to change.
Yes. Okay. Now I see it.
All right.
Thank you.
Yeah. Okay. So.
Oh, one more thing. Are we allowed to have a paper again or no?
Yes. Dr. Noveron is giving you instructions. It should be in an email. He's giving you instructions to have a cheat paper written on both sides. You can write it on both sides. And as long as you show it, you should be fine.
Thank you.
Sure, what Corina just said, make sure to show everything that you have on your desk during the exam, just so that when these recordings are viewed, we see that everything was fine. Okay, so yeah, make sure that calculator, periodic table, I think he allows you to have one, just the one that's offered in your workbook preferably, and yeah, your 1-page cheat sheet, I guess. But yeah.
Thank you.
Just don't open the workbook. This is not a open book exam, except for your cheat sheet.